Hello everyone, this is Dr. Young, and in this video we're going to introduce the reduction-oxidation reactions, also known as redox reactions. And we're going to talk about how to assign oxidation states to most compounds without having to memorize a whole bunch of random rules. So just recall that this is part of our series about different types of reactions, right? We talked about different ways you can sort them. Again, this video is all about redox reactions, which is going to be this type of reaction. And so hopefully by the end of this video, well, actually maybe not the end of this video, but the end of the next video, you'll be able to identify a redox reaction and compare and contrast it to things like precipitation reactions and acid-base reactions, things like that. So reduction-oxidation reactions, or oxidation-reduction reactions, you'll hear both, right? It doesn't matter which one's first. But we commonly call them together redox reactions, right? For reduction and oxidation. So we kind of mix the two together. I have up here an example of a redox reaction where you have, right, this is just iron and oxygen from the air makes rust, right? This is basically just rust, and I'll write that for you. This is a compound in rust, which is, right, like this rusty truck right here. Redox reactions occur all of the time in the real world. They're super important, and super important. As far as humankind is concerned, really important in the smelting of ore, right? You know, the different minerals to make pure metals, right? There's not a lot of just iron sitting around as iron. It's usually these iron oxides or sulfides or something like that. Same thing for copper and all kinds of metals. Like I just mentioned before, everyone's seen rusted metal before. That's definitely a redox reaction, that process of rusting, whether it's, copper turning green or iron turning red, that's rusting. Those are oxidation reactions. Fire, we all know fire. Fire is a redox reaction. Combustion, technically combustion is a type of redox reaction. But combustions, fires, those are redox reactions. Importantly for us, right? Importantly for all living things, metabolism, right? The way that plants can take sunlight and water and carbon dioxide and turn it into sugars, that is a redox reaction. Us eating those sugars and taking in oxygen and breathing out carbon dioxide and water, that's a redox reaction, right? We function, we're basically big old redox machines. It's what we do, it's how we work. It's how we get energy out of things. And other examples, I mean, this is not an exhaustive list, but like batteries, for example, right? The lithium ion battery in your phones, the lead battery in your car, or maybe you have a hybrid and it's got some sort of nickel battery, nickel cadmium or something like that. So also batteries. And I have over here a picture of a flow battery, which is going to be a really big thing coming up in the future, just because flow batteries can be gigantic, and that will help us store energy from solar and from wind, which are not consistent sources of energy, right? They only work when it's sunny or when it's windy. But what you can do is you can store that energy into this giant flow battery where you have fluids actually flowing from side to side. I don't have that really drawn in here, but flow batteries are really cool. If you're interested in materials and stuff like that and you care about green technologies, you should look into flow batteries. It's really going to be really important. Now, the key thing about redox reactions is that they are a transfer of electrons. Right? Remember that acid-base reactions were a transfer of a proton, right? A hydrogen, an H+. These are transfer of electrons. So in one of them, an atom is going to gain. So one thing is going to gain electrons. And one thing is going to lose electrons. And I might as well put this here now. If you gain an electron, that's called being reduced. If you lose an electron, that's called being oxidized. And we'll talk more about those terms in the next video. But the idea here is that these redox reactions, the reason we call them redox reactions, I need to put a parentheses on that, is that these oxidations and reductions always occur together. Right? If one thing is going to gain an electron, it must be that some other thing lost it. Right? So one thing gains, one thing loses, and so we see them paired up all of the time. There's no such thing as something where only an oxidation reaction occurs. They come together, so hence why we call them redox reactions, and why I will call them redox reactions pretty much from here on out. And what you're going to see is it's a transfer of electrons, and you're going to see a change in the oxidation state. And that's what the rest of this video is kind of about, is talking about what is this oxidation state. And I can look at this battery here and see that I go from vanadium 2+, I have vanadium 2+ and vanadium 3+, or vanadium 4+ and 5+. and we're changing the charges, we're changing the oxidation states on those atoms. Now, a charge is not the same thing always as an oxidation state, but they're very closely related, and that's what I want to talk about. So oxidation states. First, it was sort of coined as a term to describe how much a given atom had reacted with oxygen, hence the term oxidation. And so things that were bonded to a lot of oxygens or things that started to become more bonded to oxygen were considered to be oxidized. They had a higher oxidation number, higher oxidation state. And so if you look at this example, right, so we're talking about reacting with oxygen, here this nitrogen is bound to just one oxygen, has one oxygen. Here, this nitrogen has two oxygens. And so we would say that this one is more oxidized. And like that example that I showed you before with the iron rusting and everything, you'll notice that the iron was by itself, oxygen gas was around, and it became the iron oxide. That would be iron becoming more oxidized because it started to gain bonds to oxygen. Now, so that's kind of where it came from, is this idea of reacting with oxygen. But that's certainly, oxygen is not the most important thing here. It's just the idea that when you react with oxygen, you lose your electrons, and so you get more oxidized. And again, we'll talk more about that in a little bit. So nowadays, the oxidation states really describe how, or they describe the charge, or at least the hypothetical, the theoretical charge that would be on an atom if all the bonds were broken. So for us at this point, we really haven't talked about all the bonds, what they look like and everything, so we can't get too into it at that point, but it really answers the question of like, to whom do the electrons belong? So if we look at a bond between two atoms, who gets the electrons? So like, for example, if I have carbon and fluorine, a CF bond, the idea is that fluorine owns the electron. Owns these two electrons in this bond. They kind of belong to fluorine. And that's just because fluorine is more electronegative, right? It pulls harder on electrons, it wants electrons more than carbon in this case. So in this bond, really those two electrons belong to fluorine, not really carbon, and so we give them charges kind of based on that idea, and we're going to see that more in a second. And so the higher an oxidation number is, the more oxidized it gets. The lower an oxidation is, the less oxidized it gets. So if I was to put oxidation numbers in, let's say for these nitrogen examples, here my nitrogen is a +2, and here my nitrogen is a +4. And so that should correspond to what I just said, right? The higher the oxidation number, the more oxidized it is. Here the oxidation number of N is 4. Here the oxidation number of N is 2. So 4 is higher than 2. 4 is more oxidized than 2, right? This is less oxidized. Now the question is, where on earth did I come up with that number? I just put a +2 and a +4. Where did I get that? How did I get that? How do we determine what those oxidation states are? How do we calculate them? So you're going to see three different things. You're going to see pure elements, you're going to see ionic compounds, and you're going to see covalent compounds. So let's talk about the three of those just in order there. For pure elements, right, so they're not with anything else, they're just by themselves, super duper easy. All pure elements have an oxidation state of 0. So if I see an element, I know that the oxidation state is going to be 0. So if I look at an equation, here's sodium, that's an element. Here's oxygen, that's an element, right? It's just by itself, only one type. Here I have sodium oxide, though, that's a compound. So using what we just said, oxidation state is 0, that means I get to put a 0 for the sodium and a 0 for the oxygen. And we usually put the oxidation states kind of like where we'd put the charges for something. Sometimes right above the element, or sometimes where the charge would be in that sort of upper right-hand part of the symbol. But I don't know yet what the oxidation states are of the sodiums and the oxygen atoms in this compound. I'm going to come back to that. If it's by itself, though, I do know that it's 0. And that's true for all elements, whether you're talking about iron or nitrogen or vanadium or gold or any element. That is true. If it's by itself, it's 0. Now, if you have an ionic compound, it's also pretty easy. It's just going to equal the charge. And we know what the charges should be on things, right? We've already named ionic compounds. We know how to go back and forth between the charges, use the periodic table. It's those same exact rules. So again, I'm going to look at this one. Here I have, once again, an element. This is the same formula. Let me write that a little bit better. Another element. And a compound. So figuring out the oxidation states for the sodium and oxygen is easy because it's their elements, so it's 0. But here I do have an ionic compound, right? And let me put that, I'll put ionic compound. And so what I do is I just figure out what the charges would be on those ions, right? So you always start with the anion, or actually in this case it doesn't matter. Oxygens, right, those are always -2s, and each of these sodiums are +1, right? Just from the periodic table, everything in group 1 tends to form +1 ions. Everything in group 7 tends to form -2 ions. And that's all it is. So that means my oxidation state then of this oxygen is -2 to match the charge. And the oxidation state of each of the sodiums is a +1. So I'll just put a +1. And you'll note that there's 2 of those sodiums, so altogether it's a +2 and it all balances out. But each sodium ion only has a +1 charge, so then we give the oxidation state as being a +1. If I go down to the second one, similar issue, right? I've got an element, compound. So the calcium's an element, so I know that's 0. Cl2 is an element, I know that's 0. Calcium chloride, once again, is an ionic compound. So the oxidation states are the same as the charge. Chlorides, I know, are always -1. Calciums, I know, are always -2. That's all. That's it. So there's all my oxidation states, right? And you'll notice that the oxidation states change. And again, we'll talk about that in the next video. Calcium was 0, now it's +2. Chlorine was 0, now it's -1. That's how we're going to be able to tell that something's a redox reaction. But again, more of that coming up. So for pure elements and ions, it's pretty easy. It's already skills that we have. For molecules, it's slightly different, but still things that we kind of already know. So for molecules or covalent compounds, same thing. It's really all about electronegativity. And you just want to remember, right, that as you move up and to the right, things get more electronegative. Down and to the left, you get less electronegative. Right? Remember that electronegativity describes how much does an atom want electrons, how hard does it pull electrons, what's the strength of its attraction to electrons. And oxidation states, right, are trying to describe kind of the same thing, namely, in a given bond, who has more electrons, who has fewer electrons. So for molecules, we have kind of 2 steps. The first thing you want to do is assign the oxidation state of the more electronegative atom. Whichever atom is more electronegative, and then you just assign that as the charge that would be on that atom, in that ion. So like, for example, I have nitrogen and oxygen. Oxygen is more electronegative. Oxygen is more electronegative. So I'm going to assign it the charge that it should have if it was ionic. It's not ionic, but the charge that it would have. Oxides are -2s. So that means I'm going to assign oxygen as being a -2 here. It's the more electronegative thing. It's going to get the electrons it wants. I'm assigning it as a -2. Then what we do as sort of a second step is that we then have to deduce the oxidation state of the other atom, and we have to make sure that the overall charge matches the oxidation states. So what does that mean? So then I have to do this one, right? I have to deduce this. And I just got to make sure that the overall charge matches. So if I look at this, right, I have overall a -2 from the oxygens. I see that overall, this is overall neutral here. I don't see, like, it's not like over here with the sulfate. See how the sulfate has a -2? Sulfate overall is -2. Carbon dioxide overall is 0. Nitrogen monoxide is overall 0. So if it's overall neutral, if it's overall 0, then I know that the nitrogen must be a +2, right? Because this has to equal 0. And that means that my nitrogen then must have an oxidation number of +2. Because all the oxidation numbers have to match the overall charge. So my nitrogen is going to be a +2, my oxygen is going to be a -2. If I go to carbon dioxide, I do the same thing. Start with the more electronegative thing. I know all those oxygens are minus 2s then. So I'm going to have to deduce what the charge on the carbon must be. Here I have negative 2 charges on the oxygens, but again, there's 2 of them. So altogether there's a negative 4. But I know that overall this has to equal 0, right? We're saying that it's carbon dioxide's overall 0. It has no net charge. So that means that if I deduce what the charge is, if I have to calculate it, that must mean that the carbon must be a plus 4. Carbon must be a plus 4 to balance out those negative 4s from the oxygen. So that means that I would assign a plus 4 to this carbon. And then that all balances out. Carbon's plus 4. The 2 oxygens are each minus 2. So we have negative 4 and positive 4. That's 0. Now, if I go over to something over here like the sulfate, SO4 minus 2. Sorry, I didn't mean to make all of the second ones oxygen. That just kind of happened. But same process. Again, of these two, sulfur versus oxygen, oxygen is more electronegative, so I'm going to assign it first. I know that those are minus 2s then. Again, just based off the periodic table. And here, right, negative 2s, but I have 4. I have 4 of those oxygens, right, because of that subscript. So now there's a negative 8 charge. The difference with this one is that it's not overall neutral, right? It's not overall neutral. The overall charge is minus 2. Which means that I need to make sure that these oxidation states equal out to being minus 2. Or in other words, the sulfur, how many positive charges must I have? The sulfur must be plus 6, right? Because plus 6 and minus 8 would be a minus 2. And so that means my sulfur here must be a plus 6. And that will make it so that the charges overall equal negative 2. That's what we're doing here. So we're going to do some practice. Let's practice this. Here's a whole bunch. I want you to write the oxidation state of every atom below. You will need to get out your periodic table. Go ahead and pause here and see what you can do with these, whatever, nine problems. Okay, so I'm going to go through these kind of quickly. I'll take my time on some of the slower ones. But here I have sodium chloride. That's ionic, so I know the oxidation states are just the charges that are on those ions. Easy. H2 is a pure element. 0. Easy. So here I have water, which is a covalent compound. So I'm going to do the more electronegative element first, which is oxygen, which is a minus 2. And then I have to deduce what the hydrogens are. I'll go ahead and write this out like I did before. Right, if the oxygen's a minus 2 and overall I have no net charge, that must mean there's 2 positives. And I have 2 hydrogens, so they're each plus 1, right? One hydrogen's plus 1, the other hydrogen's plus 1, that adds up to plus 2. Here I have IBr. That's a covalent compound. Br is more electronegative than iodine. So that means I'm going to assign it its charge of minus 1. And therefore the iodine must have an oxidation state of plus 1. Right? Notice that iodine does not have the same charge that you'd expect just because it's another halogen. The iodine is going to be a plus 1 because it's in a covalent bond. We're saying that bromine basically kind of hogs the electrons to itself, not iodine. So it has iodine in this case has a plus 1. We have manganese dioxide. Manganese, again, is the more electronegative element. Assign it its charges, which would be minus 2. I have 2 minus 2s. That has to equal 0, right? That negative 4. So the manganese here must be a plus 4. So manganese 4 plus. If I go over to vanadium, same story. Oxygen still is minus 2. So minus 2, but there's 3 of those, so minus 6. Vanadium must be a plus 6, so I put the oxidation state of plus 6 on the vanadium. Here I have sulfur. Sulfur is more electronegative than hydrogen, so minus 2 here. This is going to be a lot like the water one, where I have a minus 2. That has to be a plus 2, but there's 2 hydrogens, so they're each a plus 1. If I go over to ammonia, this one I need to pay attention to. Sorry, sulfur was more electronegative. In my ammonia, I have to watch out because the more electronegative one is actually first, not second in ammonia. So it's actually NH3, but nitrogen is more electronegative. So I'm going to go ahead and give nitrogen the minus 3 that it should have because it's a group 5. But that makes all of these hydrogens each a plus 1. So all of those hydrogens would be a plus 1. Same deal here, right? The nitrogens are a minus 3. This has to equal out to 0, so there must be 3 positives, but there's 1, 2, 3 hydrogens, so they're all plus 1s. And then lastly, over to this nitrogen oxide, dioxide, we have oxygen is more electronegative. So -2 for the oxygens. There's 2 of those. Equals -4, 0. Therefore, the nitrogen in this case must be a +4, which is what I did in that example early on in this little lecture here, right? When I figured out, oh, the nitrogen must be a +4. So in theory, you should be able to go back a few slides, right? Go back a couple minutes here to those examples when I first was talking about the 2 nitrogen compounds and one being more oxidized than the other. And you should be able to figure out that these oxidation states, what these oxidation states are and how they changed. So we're going to use this skill so that we can determine a few things. One is a reaction, a redox reaction. 2, if it is a redox reaction, what thing got oxidized, what thing got reduced? And then 3, how we'll write half reactions, which are specific basically just to redox reactions. So practice this some more. If this doesn't make sense, email me if you have questions. Good luck. Watch the next video on how to use this to determine what gets oxidized and what gets reduced.